Hello, and thank you for listening in. My name is On Iftikhar, and I'm a Senior Solutions Architect at AWS. I work with healthcare customers in Australia. I'm joined by Mustafa Sheikh, Senior Data Scientist at eHealth New South Wales. Today, we will go through some ideas of how you can build model ensembles on Amazon SageMaker to improve the accuracy of your predictions. We'll dive into how New South Wales Health is leveraging this technique for a critical, potentially life-saving use case. You can expect to walk away from this session with an understanding of the considerations for implementing machine learning in the real world and leveraging techniques like ensembles to enhance predictions. We'll start off with a brief overview of the process of ensembling machine learning models and how you would go about doing it with Amazon SageMaker. We will then go into the sepsis management use case being implemented by New South Wales Health, which will be followed by a deep dive into the architecture and implementation. We'll close off with a view of what's next for this project and resources to help you get started with your journey with Amazon SageMaker. Before we get into the details, let us quickly refresh our memory on Amazon SageMaker. SageMaker is a broad set of machine learning capabilities and services to help data science teams be more productive, building, training, and deploying machine learning models. SageMaker provides all the components used for machine learning in a single toolset, so models get to production faster with much less effort and lower cost. You can build machine learning models at scale and get them ready for training with everything you need, from label training data, access, sharing notebooks, using built-in algorithms and frameworks. Train machine learning models with everything you need to train, tune, and debug these models to achieve maximum accuracy. Deploy machine learning models in production on a fully managed infrastructure with constant monitoring to maintain high quality. What exactly is model ensembling? It's essentially a machine learning approach to combine multiple models in the prediction process. The requirement to combine models stems from the fact that often in practical applications of machine learning, a single model has weaknesses. By combining or averaging predictions from multiple sources or models that have different strengths, we can get an improved prediction. This is usually to overcome challenges where a single model suffers from high variance, low accuracy, or bias. Hence, with model ensembles, there are two main objectives: reducing the prediction error and maintaining generalization of predictions. Let's have a look at how model ensembles are actually implemented. The process of ensembling machine learning models includes two steps: training different models and combining the predictions. You can obtain different models by using different model architectures and algorithms, feature subsets, training data, and training regimes. As with the standard machine learning approach, you can train these models against either a full or a subset of your training data. And depending on the technique adopted, the training of the different models can take place in parallel, or it can be implemented in a sequential process, with each subsequent model attempts to reduce the errors made by prior models already added to the ensemble. Once the models are trained and deployed to serve predictions, we can now start to make predictions across the model ensemble. We adopt an aggregation method to bring together the output from each of the models. And you can combine these predictions by averaging them, using weighted averages, or training new models on top of the predictions, a technique known as model stacking to get to your final prediction. Let's refresh on how training models and hosting models works with Amazon SageMaker before we dive into the use case. You can train models using Amazon SageMaker training jobs. It provides an easy way for zero setup, distributed, and managed training. When you create a training job in SageMaker, we actually spin up a separate environment for you, which includes provisioning new instances, loading a container which has the algorithm code onto them, bringing your data in from S3 or mounting it via EFS or FSX, training the algorithm, saving the model artifacts back to S3, and then tearing down the cluster without you having to think about managing or orchestrating the workflow yourself. This is the best place to run long-running model training jobs, as you can optimize the compute time and performance. And all of this is built to use existing technologies that you may already be using or used to, like Docker containers. Every algorithm in SageMaker, whether it's a customized pre-built algorithm or it's one you bring yourself, is a Docker container that's stored in the Amazon Elastic Container Registry. The same method can be expanded to multiple models in an ensemble, which can be trained on the whole or a subset of your data. And then finally, and this goes to the SageMaker's modularity, when you've trained your models in SageMaker, you can deploy that trained model either locally to a SageMaker endpoint, or take the model artifact and deploy it wherever you want. One thing I want to highlight here is the algorithm container option. These containers use built-in algorithms like XGBoost, which are optimized. They require the least effort to get started, and they scale as your dataset is large or significant resources are needed to train and deploy the models. The New South Wales Health sepsis detection use case leverages these algorithm containers as well. You also have the option to use framework containers, where you can bring your own MXNet, TensorFlow, or PyTorch code, for example. Or bring your own container altogether if you want to run custom packages or any code which is not part of a built-in framework. Now, once the model is trained, SageMaker offers a number of options when it comes to deploying the models into production. In this case, we will leverage the persistent real-time endpoints that make one prediction at a time. This is SageMaker real-time hosting services. These endpoints are fully managed and support auto-scaling. When you use an algorithm container, SageMaker automatically creates a RESTful API around your model and then exposes that secure REST API to your customers or applications for real-time predictions. I'll now welcome Mustafa from eHealth New South Wales to walk you through their work in building a solution for early sepsis detection in the emergency department, how they're applying ensemble techniques to enhance their predictions and monitor the health of their models.
Thank you, On. I will start with what is sepsis. Sepsis is a serious medical condition resulting from the presence of harmful microorganisms like virus or bacteria in the blood or other tissues and the body's response to their presence, potentially leading to the malfunctioning of various organs, shock, or even death. Patients arriving in emergency department or ED with possible septic condition may have on average a 20% risk of death. And if not treated timely with antibiotic, the risk of death may increase to 40%. In Australia, there are about 5,000 deaths per year, while underlying primary cause is sepsis, and more than 15,000 patients get admitted to ICU annually due to septic shock or severe septic condition. This project aims for earlier detection of sepsis among the patients waiting in the ED. I'm going to provide a brief workflow of the patients within an ED along with the AI-driven predictive sepsis system. As a patient arrives at the ED, usually a triage nurse consults with the patient, checking the patient's vitals like heart rate, oxygen saturation, blood pressure, temperature, etc., and their presenting condition. These observations are recorded into electronic medical record system. The predictive sepsis system gets the data entered into the electronic medical record in near real time and provides a list of patients who are at risk of sepsis waiting at ED room. The front of house coordinator reviews the at-risk patients and then places patients onto sepsis pathway treatment. Hospitals of New South Wales state already have rule-based sepsis detection system called Sepsis Pathway in place, but the manual form-based approach is not free from limitations, which are the conditions to flag sepsis are consisting of a static boundary of several vital signs, which often fails to flag true positive cases, that is low sensitivity. Since this is a paper-based approach, clinicians need to calculate the risk manually, which is often difficult to interact with the patient's condition and vital measures. Undoubtedly, ED is a very busy environment where pen and paper-based approach adds another level of complexity. From historical data, we have observed that the paper-based system could flag only 2 to 2.5% of the ED presentations as true positive, with higher degree of false positives that often causes alert fatigue with the ED nurses. But in reality, there are about 5 to 7% of the presentations which are sepsis related. Therefore, there is a room for improvement on the current rule-based system, which this project aims to address. Through an AI-based system, we are aiming to improve a few things like apply a clinical definition of sepsis in the model, which will increase the detection of true positive cases, that is high sensitivity, and miss fewer cases. reduce alert fatigue by improving the prediction specificity. The system will get the individual's input values of the vitals directly from the electronic medical record system as they are entered by a clinician. The system will then readily calculate the risk of sepsis. This project is a real example of how artificial intelligence can help clinicians within the 24/7 emergency department. It is helping make real-time decisions from electronic medical record data. Overall, AI is going to make clinicians by consuming huge volume of clinical data and then condensing this into bite-sized information, presenting personalized recommendations and intelligent data to support decision-making at the point of time required. The project is currently at a clinical pilot stage, and in order to measure the success of the project, we have set up a few KPIs. These are reduced time to treat with antibiotics, reduction in transfers from the ED to ICU, less readmissions of the patients who visited ED within 60 days appearing with this septic condition, and finally, a reduced number of deaths. A Bayesian structural time series model is being used to contrast the impact of our tool against similar sites without it, to account for any macro trends that are occurring. The AWS model monitoring system is helping us keep an eye on models' performance metrics. Let's have a look into the solution architecture and how AWS SageMaker has been utilized in this project. The project has passed through different stages, and I'm going to provide some highlights of each. To train and build models, we have used an historical extract from the electronic records of patients who visited EDs from various hospitals across the state. Clinicians and the human-centered design team were consulted to observe the ED workflow and process. Their inputs and recommendations were incorporated to develop the clinician-facing dashboard. Patients' data from electronic medical record is delivered through a real-time integration as the input to the system. Several rounds of user acceptance testing have been conducted with clinicians, and post-UAT feedback helped to deliver the clinician-friendly dashboard. We are in the process of evaluating the performance of the model in response to real-world cases, as well as measuring benefit of implementing the system. What you see here is the dataset and processes applied to develop the models. 3 years of historical electronic medical record of hospital patients from 4 emergency departments were extracted to label the dataset into 2 categories, sepsis or no sepsis. We have applied a clinical definition of sepsis through domain experts to label each observation. We have noticed that the prevalence of sepsis increases the older a person is. At present, we have a rule-based system to identify sepsis, but our intention with this project is to apply supervised machine learning models for better performance to correctly identify patients with sepsis, that is higher sensitivity, and those without sepsis, that is higher specificity. This is a 2-class classification problem, and after experimenting with various classification models, finally we have employed XGBoost, linear learner with binary classifier, and logistic regression to train the classifiers to detect sepsis or no sepsis cases. Our dataset is very much unbalanced. Only 8.33% cases of about 500,000 observations are positive. Therefore, we have experimented with different probability thresholds to achieve our desired score for sensitivity and specificity. The third international consensus definitions for sepsis and septic shock, known as Sepsis 3, requires a score called SOFA. SOFA stands for Sequential Organ Failure Assessment. SOFA numerically quantifies the number and severity of failed organs like brain, heart, kidney, liver, etc. In order to calculate SOFA score for each observation, a pathology report is required. Since this was retrospective data, the necessary pathology report data were available to calculate SOFA score and apply the Sepsis 3 definition to label the dataset. For a patient in the emergency department setting, there would be no pathology test result. Therefore, the predictive sepsis model should only rely on a patient's vital measures like blood pressure, oxygen saturation, temperature, etc. For this reason, we have considered only the vitals observation to train the models. These vitals are usually recorded by the clinicians while a patient is assessed by an ED nurse. Here we have shown the list of features in color that are used to train the models. The white color variables are kept for exploratory data analysis and reporting purposes. This shows a high-level system architecture on the AWS cloud. As soon as a clinician inputs the vitals measurement of a patient in the electronic medical record, the information is delivered through a real-time integration to an S3 bucket as HL7 formatted messages. HL7 message is a structured data format and is a messaging standard that enables clinical applications to exchange data. As soon as the HL7 messages are put into S3 bucket, a Lambda function is triggered. The Lambda function does three things. Firstly, it works as a parser to parse HL7 messages and extract the required feature and associated values, for example, age, systolic blood pressure, temperature, etc. Then it invokes the model endpoints deployed through AWS SageMaker. From the endpoint response, it processes the output response. Finally, it saves the feature set extracted from HL7 messages along with the model's score for the observation in an Amazon Aurora database. The clinicians log in through single sign-on system to access the patient listing displayed on a clinician-friendly dashboard. The dashboard is deployed on a Tableau server and it has a live data connection with the database to display the data in real time. As previously mentioned, there are three models deployed. Two models, namely XGBoost and Linear Learner with Binary Classifier, are built using AWS SageMaker container provided models. These two models are deployed through SageMaker endpoints. The other model, logistic regression, is implemented through a Lambda function. The endpoints and logistic regression model are invoked from a Lambda function with the payload extracted from incoming HL7 message. Each model predicts the expected class for the same payload passed onto them by the Lambda function. While each model predicts the expected class to be either 1, representing sepsis, or 0 for non-sepsis cases, the models also provide the probability score of the decision made. If at least two models score an observation to be 1 or predicted as sepsis, then final level for the given observation is set as sepsis. The highest probability is taken to indicate as the percentage risk of sepsis on the dashboard. We have used SageMaker Clarify to explain XGBoost model. In this slide, the SHAP values are displayed for the XGBoost model. SHAP stands for Shapley Additive Explanations and used for machine learning explainability. SHAP values are used to understand what decisions the model is making and why. The positive values contribute to the increase in final probability and negative values contribute to decrease it. From this perspective, we notice that the top 5 features are oxygen saturation, age, temperature, Glasgow Coma Scale, GCS, and systolic blood pressure. We also understand the higher values of oxygen saturation reduce the chance of positive sepsis, while higher body temperature and age increase the risk of sepsis. Our aim is to get machine learning models to work better than the current rule-based system. And in order to measure that, our two metrics are model sensitivity and specificity. Sensitivity indicates the ability of a test to correctly identify patients with suspected case of sepsis, and specificity indicates the ability of a test to correctly identify people without the condition. A good specificity would reduce alert fatigue, while a better sensitivity would work as a good blind spot detector in this context. The hyperparameter-tuned XGBoost algorithm achieved a sensitivity of 77% and a specificity of 84% across all age groups. Since we have found a positive prevalence of sepsis with respect to age, we divided our population into 3 age categories as 16 to 35, 36 to 65, and 66 to 115 year range. From explainability analysis, we have found that XGBoost model worked better for mid to old aged patient cohort. The built-in linear learner binary classifier algorithm achieved a sensitivity of 72% and a specificity of 84% across all age groups. From further experimentation, we have found that linear learner model also worked better for mid to old aged patient cohort. Both XGBoost and linear learner models obtained a decent specificity, which would be promising to reduce alert fatigue in the busy emergency department. The logistic regression model obtained a sensitivity of 80% and a specificity of 61% across all age groups. Though this model got a good sensitivity with poor specificity, but this model is more explainable to explain the individual contributions of each feature to classify a case to be either positive or negative. From further experimentation, we have found that logistic regression model worked better for a younger patient cohort. Since there is no clear-cut winner in terms of these 3 models, we have taken all the 3 models to score the same set of observation in the ensemble approach mentioned before. In order to check the model's health, we have developed a reporting interface where the 2 metrics, sensitivity and specificity of the models, can be reported from the live dataset. So how does it work? The evaluation is compiled by a month lag. The real-time data coming via HL7 messages are processed and classified by the models, and predicted classification results are saved into the database. For each month, we obtain the extract of the medical's record from the system, and the ground truth of those observations are obtained to check the predicted decisions. SageMaker model monitoring is set to notify when there are deviations in the model quality. Model Monitor provides drift in data quality as well as drift in model quality metrics, sensitivity and specificity. This shows the clinician-facing dashboard. Since emergency department is a 24/7 service, the dashboard also works in sync with this operation and reflects the up-to-date timely information. It shows the current list of patients waiting in the emergency department along with their name, age, identifier, vital signs, measures, and the predicted ML decision shown in suspect column. This is working as a blind spot detector to the clinicians for the patients who may be apparently looking healthy but might develop a risk of sepsis if not addressed earlier. Through this dashboard, clinician can look at the most at-risk patients and, if required, double-check their vitals and may apply early interventions like providing antibiotic or performing a blood gas test to reduce the risk of sepsis. This shows a schematic report to reflect the benefit of the system by measuring the 4 KPIs we mentioned earlier. This is a pilot system currently deployed at ED setting of one of the hospitals of NSW. In order to validate the KPI measure, we have applied a Bayesian structural time series causal impact model to contrast the impact of this system against similar sites without it. From this perspective, we are expecting a reduction of measure across all the 4 KPIs. In order to take the project to next level, there are few plans ahead. Firstly, collect the user acceptance from the real-world deployment and use cases. Final user acceptance testing is occurred through February and March, followed by a clinical go-live. The pilot will run through to August with an agile development model, and then looking into the model benefit in terms of those 4 KPIs mentioned. If the clinical pilot is able to demonstrate significant improvements to patient outcomes, eHealth New South Wales will partner with a clinical organization within NSW Health and develop a business case to scale the solution to additional hospitals. We may look into the revise the ensemble function with a weighted factor depending on the age of a patient. Also, there is always a room for improvement of the models by incorporating new features and more training data. This project is being completed with multiple collaborators as shown in this slide. I am acknowledging their contributions and efforts to make the project a success. Many thanks and gratitude to all of our collaborators. Now I am handing over to On and thanking him sincerely for providing this opportunity for show and tell about this predictive sepsis project. Thank you.
Thank you, Mustafa. Those really were some great insights. It's really exciting to see how eHealth New South Wales, in collaboration with their partners, are applying the power of machine learning to drive a life-saving outcome for clinicians and patients. I'd like to leave you with a few resources to get you started. These are links to Amazon SageMaker example Jupyter Notebook Library, walkthroughs of building a model ensemble, and custom container images. Leverage these to your advantage and get your hands dirty, learn from them, and build on top. And to continue your cloud learning journey, please use these training resources to build and validate your skills. Thank you for attending this session, and we hope you found it valuable and learned something new. Before you go, please take a minute to complete the survey and provide us your feedback. Let us know what you think went well and how we can improve these sessions in the future. We really value your feedback. Thanks again. Enjoy the rest of the summit and have a great day ahead.